In today's lesson, we will be introducing rational functions. So this is chapter 9 in our textbook, but it's part of unit 2 in our workbook. A rational function is defined as a function that has a polynomial in the numerator and a polynomial in the denominator, with the restriction that the polynomial in the denominator cannot be 0. You can graph a rational function by creating table of values, and the way that we do this most effectively to get the visual of the graph that is most accurate is by identifying any non-permissible values in the denominator. So this is, what can x not be so that the function in the denominator is 0? Right? Because we don't want a denominator of 0. So we're identifying what are the x values that would make the denominator 0, and those are non-permissible values. We're going to be shortening that to NPV. Write the non-permissible value in the middle of your table, and then find some numbers, positive and negative, or to the left and to the right of your non-permissible values, above and below in the chart, and I'll do a demonstration of this in a moment. You want to make sure that you have some small numbers and large values of x so that you get a really good big picture idea of what your graph looks like. Now in unit 1, we talked about the base function 1 over x, and we knew what that looked like. Our base function for 1 over x looked like this, with key points at -1, -1, and 1, 1. However, when we do a transformation, our new equation will look like this, where A represents our vertical stretches, H represents our horizontal shifts, and K represents our vertical shifts, just as before. So for example, if I have this equation here, y equals 3 over x plus 4 plus 5, the values of the parameters are that A is 3, H is 4, and K is 5. And so we know what those representations are in terms of stretches and translations. One of the things that's going to be new and really handy in this unit is that the vertical asymptote will be represented by H, and that the horizontal asymptote will be represented by K. So right from looking at that equation, I can see that I have a vertical asymptote at my non-permissible value, x equals -4, and I have a horizontal asymptote at my K value, x plus 5. So essentially what I'm doing is I'm taking my base function where I know that I can't touch 0 because I don't want a 0 in the denominator, and I'm moving it up 5 and left 4. So I'm moving my asymptotes here so that my new graph will look like that. And that's what you see in the picture of the graph here. This is the base function y equals 1 over x with asymptotes at 0, 0. And then after we shift it, here's my new asymptotes at -4 and +5. And the shape of my graph shifts also. There is a stretch here of 3. However, when you think of the mapping notation, right, we have x, y mapped to, let's see here, x minus 4, 3y plus 5. My asymptotes are at y equals 0, the original one. So when I put a 0 in here, the stretches don't really affect it because anything times 0 is 0. So only the horizontal and vertical shifts affect the asymptote. So we can always kind of know where we're starting off with just by looking at the equation. Now, some of the equations are not going to be in this form. We always want it to be in this form because we can get a lot of information from looking at it that way. But we're not always going to get that. So we're sometimes going to get an equation that looks like this. Here's an example. And we can use some algebra in order to manipulate this in order to make it look like that. So what we want to do essentially is we want to create a situation where we can essentially split these into two. So anytime you have two things in the numerator, and this only works with numerators, not denominators. I'm going to say that right now. When you have multiple things in the numerator, you can actually split this as 3x over x minus 4 plus 6 over x minus 4. Now, in this piece, I don't have any x's, so this piece is going to represent that part of my equation. And what I want is to manipulate this piece so I can factor out that 3 and simplify it a little bit to get rid of x minus 4. And the way I'm going to do this is if I were to say a bracket here, x minus 4, if I could do that, then what number am I adding in the pink? This would be the same thing as adding 3x minus 12 over x minus 4. However, I can't just add numbers randomly, right? I have to add them strategically. So if I'm minusing a 12 in here, that means I'm going to add the 12 in here, x minus 4, because I want to manipulate the way that my function looks without actually changing the value. So what I've done here is I've said I'm going to minus 12 from the equation and add 12 from the equation so that the result of what I've changed is actually 0, but it helps me manipulate what it looks like without changing the value. Okay, so I'm choosing numbers where I can now do this. If I factor the 3 out of the top, I get an x minus, oopsie, minus 4 in the numerator, x minus 4 in the denominator, plus, this is going to be 18 in the numerator, x minus 4 in the denominator, and on this side, I can't change anything. It is what it is. But over here, I have an x minus 4 and an x minus 4, and this simplifies to just 3. So now I have an equation that looks like that. 18 over x minus 4 plus 3. So this means I have an a value of 18, which represents a vertical expansion. I have an h value of 4, which represents me moving the graph to the right 4. And I have a k value of 3, which represents the graph moving up 3. Okay, so if we have an equation that doesn't look like the transformation standard form, then we can split the numerator and choose what number can we add and subtract. It's got to be an add and subtract because we want it to be a net 0 so that we can kind of manipulate the function to make it look like that. Okay, so my horizontal asymptote is going to be 3, and my vertical asymptote is going to be 4 in this case. So I know where I've shifted my graph. In example 1, let us graph the function y equals 4 over x using the table of values. Okay, so first thing I'm going to notice here that I have an a value of 4, which represents a vertical expansion of 4, but I have a horizontal shift of 0 and a k of 0, so I know that these are going to represent my asymptotes. Okay, so my non-permissible value, I cannot have a denominator of 0, so x cannot be 0. When we graph the function, we want to choose points where graph the rational function of the form, and we want to choose points that approach x equals 0 and y equals 0, because those are our asymptotes. So we want to be choosing numbers that are close to that point from the left and from the right. So first thing is I'm going to use my red pen here, and I'm going to dot on my graph where my asymptotes are. 0 and 0. So I should not be crossing these lines. Next, I create my table of values. I know it is undefined at x equals 0. So my non-permissible value goes in the middle of my graph. And I want to choose numbers before the 0 and after the 0 to kind of see what's going on. So let's go -1/2. Let's go -1, -2, -4. And then I'm going to do the same values on the right side of it. +1/2, +1, +2, +4. Okay, now for my y value, this is y equals 4 over x. So 4 over -4, that gives me -1. 4 over -2, that gives me -2, -4. 4 over -1/2. Think of it as this, 4 divided by -1/2. That's the same as 4 times -2 over 1, right? When we deal with fractions, we got to remember our fraction rules. So this is -8. And the numbers for the positives, because the function is symmetric, we can just use the same numbers, but we know these ones are going to be positive. Okay? So looking at the graph, I cannot touch the 0, but if I go to 1/2, I am at +8. 1, 2, 3, 4, 5, 6, 7, 8. At 1, I'm at 4. 1, 2, 3, 4. At 2, I'm at 2. And at 4, 2, 4, I'm at 1. So here is the right side of my graph. I'm going to do the same thing with my left. 1, 2, 3, 4, 5, 6, 7, 8. 2, 4, 2, 2, and 1. Okay, there we go. That is my graph. Now we got to talk about some end behavior. It says we can check our work with a graphing calculator. I'm not going to ask you to do this on a test because that's going to take forever, but we can put it into our calculator just to double check. 4 divided by x graph. There it is. So we have the same shape. Summarize the characteristics of this graph in this table. What is my non-permissible value for y equals 4 over x? We said our non-permissible value is x equals 0. What is the behavior near the non-permissible value? So at x equals 0, what's going on in the graph near this point? And this is what we call the limit. We describe the behavior near points of interest as the limit. As the x values get closer to 0 from the left side, and we use a little negative in the exponent, in the spot of the exponent, so to mean that we're approaching x from the left. The limit as we approach x from the left, the graph f of x equals -infinity. So look at our picture. As we approach y equals x from the left side, our graph is going down, 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 down forever. So as we approach x from the left, our graph goes to -infinity. Similarly, the limit as x approaches 0 from the right, now I'm going to use the plus sign, the function goes off into positive infinity. And again, look at here. I'm getting closer to 0 from the right side. And as I do that, my graph gets taller and taller and taller. So it's going up and up and up forever. We can never touch that point, but we can observe what is the behavior close to that point. When we look at what is the end behavior, this is looking at what's happening on the far, far, far right side and on the far, far, far left side. As x goes to infinity, what is our function doing? As x goes to negative infinity, what is our function doing? So end behavior is the limit as x goes forever to the left, the function gets close to what value? Okay, so as x goes to the left forever, my graph is going up and to the left, but it cannot cross the dotted red line. So my function is actually approaching 0. It's coming up and to the left, getting close to 0, but cannot touch it. I should keep my pen the same color here. And same thing as I look at what's happening as x goes forever in the positive direction. What is the value of my function approaching? As I go to positive infinity, my graph is coming down and to the right, but it cannot cross that line, so it's approaching that line, and that line is at 0. So this is talking about behavior at the very, very far end of your graph. What is the domain of my graph? Well, I only have one non-permissible value, and that x cannot be 0. So my domain here is just that. X cannot be 0, but x can be any other real number. What is the range of my function? Same thing. I'm going up forever and down forever, but I cannot cross one specific line. So y cannot be 0, but it can be any other real number is fine. What is the equation? Equation means I need an equal sign for the vertical asymptote and the horizontal asymptote. When we look at a vertical asymptote, the equation is x equals some number, because vertically we can be at any value y, but x is always 0. So when we write a vertical asymptote, we're saying x here is 0. The horizontal asymptote is y equals 0. Again, because x now can be any value, but the y value for the horizontal line is that y is always 0. So this is our summary for this particular graph. Okay, let's take a look at a transformed function. We have a function given to us right here, and it says to compare it to the function a over x minus h plus k to determine the values and parameters. So what's going on here? A in this case is a 3, so that represents a vertical expansion. H is positive 3, so that means I have a horizontal shift right 3, and this also is telling me my vertical asymptote now is at y equals 3. Sorry, x. No, y. Y is correct. Pardon me. Did I do that right? H is a horizontal shift. Yes, vertical asymptote is at 3. And then I'm sorry, my last piece here, K equals 2. So I have shifted the graph up 2, which represents a horizontal asymptote at positive 2. Okay. Now, if the asymptotes of 1 over x are at 0, 0, use the above to figure out what are the new asymptotes. Well, we just did that here, right? Because our asymptotes are not affected by reflections and stretches. They are only affected by horizontal and vertical shifts. So we start at 0, 0, and we shift them to whatever directions H and K tell us. Okay, will this graph have an x-intercept and a y-intercept? And the answer here is yes, because in our original graph, y over x, we cannot cross the line of y and x equals 0. However, in our shifted graph, we have our asymptotes. I'm going to draw them in red. They have been shifted up 2 and to the right 3. So now the pink represents the pieces that I cannot touch. So my graph will be somewhere over here and somewhere over here. So because we shifted our asymptotes, I'm going to cross over at this point and at this point. Well, how can we determine the intercepts? Remember that when we look for the x-intercept, we let y equals 0 and we solve for x. And when we look for the y-intercept, we let x equals 0 because we are looking for the y. So let's do that with our calculators here. So if y is 0, I'm going to need some space here. Maybe I'll just do it on the side. If y is 0, what is x? I'll have 3 over x minus 3 plus 2, and I want to rearrange this equation. So I'll have negative 2 equals 3 over x minus 3. And then I'm going to multiply both sides by x minus 3 to bring that up from the denominator. So these guys cancel. Then I'll have x minus 3 equals 3 over negative 2. And x equals 3 over negative 2 plus 3. I'm just going to grab my calculator here. 3 divided by negative 2 plus 3. That gives me 1.5, or 3 over 2 positive. So my x-intercept is at 3 over 2, 0. Did I write that correctly? Yes, perfect. Okay, and then to make my or to find my y-intercept, this one's going to be a slightly shorter equation. I'm going to have y equals 3 over 0 minus 3 plus 2. Well, 3 over negative 3, that gives me negative 1 plus 2, y equals 1. So my y-intercept is at 0, 1. Okay, so I know where my intercepts are. I know where my horizontal asymptotes are. So without doing a table of values, let's just do a rough sketch of what we think this is going to look like. So we said that our vertical asymptote got shifted to the right, 3, and our vertical or horizontal asymptote got shifted to 2 up. We have a x-intercept at 1.5 and 0. So 1.50 is here. And we have a y-intercept at 0 and 1. So my graph is going to go like this, and like that, and something like this. You could also, if you really wanted to, you could write some mapping notation here, and you could say, all right, from my original graph xy, what would this equation be? This would be x plus 3, 3y plus 2. So on my original graph, I know that 1, 1 was a point, which means it's going to get mapped to 4 and 5. And I knew that negative 1 is a point. So this is going to get mapped to 2 and negative 1. So you could add 2 more points if you really wanted a slightly more accurate graph. So 1, 1 would be at 4, 1, 2, 3, 4, 5. So I would just need to move this little bit here over. There we go. It didn't ask us to do this, so again, if it doesn't ask you to do this, you don't have to do this. But I'm just trying to show you ways that you can draw a more accurate graph if you've got time and are interested. Let me just double check my points here. Oh, my x-intercept, I put it at 1/2 instead of 1.5. It should be there. There we go. Okay. So you can always map 2 key points. You know the original is always 1, 1, -1, -1, and you know where your asymptotes are. You can find your x and y intercepts by setting the other variable to 0. And it's saying, check your graphing calculator, make sure you did this correctly. All right, let's give it a go here. I'm going to clear this. This was 3 divided by x minus 3, close the bracket, plus 2. Let's see if this matches our picture here. And there we go. Looks just like what we sketched. Perfect.